right, hello there. Today we're going to start chapter 4, and the topic of chapter 4 is on what are called vector spaces and also subspaces. So, vector space is basically what it says here, a collection of objects that behave like vectors in the real numbers. And so I just want to highlight one little thing on this page here and then talk about the rest real quickly. It says a vector space is a non-empty set V of objects called vectors on which are defined two operations called addition and multiplication by scalars. All right? And that basically when we have a vector space and you want to say that something's a vector space, scalar multiplication has to work and addition has to work, and there also has to be the zero vector, which is this guy right here. These couple things right here. But anyway, if you wanted to prove that something is a vector space, then all 10 of these must be true. And so if you wanted to go through the process of like proving each one and showing that each one works, you could do that. We're not going to do that, but we'll just kind of like summarize a little bit and say that, oh yeah, we know that this would work. We can imagine that it would work. So we're not going to do like a full-on proof of anything, but that's how it goes. All right, so some vector spaces you already know. The set of real numbers. You got a set of ordered pairs, 2 dimensions, and you have 3 dimensions. And then you have all your row and column stuff. And so these are all the things that you already know, and maybe you didn't call them vector spaces, but they are. All right, so here's a vector space example. Is a set of all vectors in R2, so 2 dimensions, of this form where you have the same number twice. And the usual definition of vector addition and scalar multiplication is it a vector space. All right, so what the easiest thing to do is to go and see if these things are true. All right, so normally you'd have to prove all 10, but we're just gonna kind of put some of them together. So like in step 1 or in part 1 up on this last page, if I add 2 vectors that are in this format, is it still in that format? So if I say something like I have 2, 2, and I add 3, 3, both those vectors are in this like format where they have the same number twice, right? And if I add that, then I get 5, 5, which is also something in that same format. All right, so that seems to be true. And we can go ahead and tack on, part 2 and part 3 to this. If we do that, I can see if I switch the addition, it's going to be the same. If I have a third vector, let's say I had 1, 1 in there and I moved them all around and added them in different order, it's all going to come out to the same answer. All right, what about in part 4? Part 4 is asking you, is there a zero vector? Well, could I just make those both 0? So yeah, I could. And also step 5. So step 5 says, like, if you pick something like 2, 2, could you find another vector like negative 2, and you add those to get the 0 vector? Yeah, you could. All right, and then you could also do number 6, scalar multiplication. Like, let's say you had 4 times 2, 2. You got 8, 8, so it's a vector in that space. So that checks out. So, and so on with all the rest. You would be able to prove them all. So you would say yes to this. Okay. All right, in example 2. It says let W, so that's our space right there that we're trying to prove is a space, is a union of the first and the third quadrants in the XY plane. And so basically they're saying let W be X and Y, such that X times Y is greater than or equal to 0. So basically any 2 numbers that multiply to something positive. So that's why they're saying the first and the third quadrant, because in the first quadrant, remember, you have 2 pluses for X and Y. In this third quadrant, you have 2 minuses. So we're trying to say if you multiply the numbers, you get a positive. So that's why they're talking about first and third quadrants. All right, so if, part A, if I pick a vector that's in this, that does this, and I multiply it by a scalar, is that in W also? So let's try it. So let's do C times a random X and Y. And so I would get CX and CY. All right, so remember, this has to be true. So if I take those 2 things, CX, and multiply it by CY, if I multiply them, do I get something that's greater than or equal to 0? All right, let's check it out. So I would get c squared xy. So I still don't know. But what I do know is this. I know that xy is greater than or equal to 0. So that's positive. And by definition, when you square something, it's greater than or equal to 0. So if you multiply two positive things, then you get something positive, right? So I would say yes to that. Okay. In part B, so that would be one of the things to prove. Do I get, one of the pieces I could prove to see if this is a vector space or not. But let's look at this one. Find specific vectors in U and V such that U plus V is not in W. So this is going to show that this W up here is not a vector space. Because what if I pick something like, I don't know, 2, 10. That's in there. It's both positive. 2 times 10 is greater than or equal to 0. And then let's say I added another vector in there. I added like -8, -1. That's in there. It's two negatives. It multiplies to positive. Right? If I add these together, I get -6 and 9. This is not in the vector space. If you multiply -6 times 9, you do not get something greater than or equal to 0. So that is a big sad face. That's why it is not a vector space. Okay, so usually what you're trying to do is just prove that you have a vector space, and that's the easiest way to do it. And then if you can't find anything wrong, then you're like, okay, it must be a vector space. All right. So what we're going to do next is there are vector spaces inside other vector spaces. Okay, and so those are called subspaces. All right. So when you have vector spaces inside of other ones, that would be called a subspace. And so what we're going to do you have to make sure something to be a subspace, the 0 vector is part of the set. If you do scalar multiplication, it has to work. And if you add 2 vectors in the set, you get a third vector in the set. So if something's a subspace, those 3 things have to be true. All right, so that's what this part is explaining right here. All right, and so what we're going to do is in example 3 and 4, try to prove that this is a subspace of R3. So it's important what you're trying to prove is a subspace of. So basically what we're trying to say here in this example 3, we're trying to show if I have a vector in this format right here, that it is a subspace of 3 dimensions. It doesn't like lose a dimension. All right, so let's see. Step 1 is a 0 vector in there. If I let A and B equal 0, do I get a vector that's a 3D thing? Or do I get a vector in R3? So if I do that, I get 0, 0, 0. So yeah, that's fine. That means a 0 vector is in my R3 subspace. Right? So step 2. Now all the A and B have to be our real numbers. So if I take something like -2, 0, and 4, and I add to it, now we're doing these with numbers. You could also do it like symbolically with like x1 and x2. And so you could make this one, x1, then 0, then x2, and try to say it like that. And then I have another one I'm going to make 5, 0, -1. So when I add these 2 things, I get 3, 0, and 3. So yeah, this is a vector that looks like this, so we're good. And third thing, if I do a scalar, if I multiply C, and so like if I try to do this like symbolically, A, 0, B, I get CA, 0 again, and CB. So what I'm kind of checking for is that 0 in the middle, does it stay 0? Because C times A and C times B, those are real numbers because C is a constant. And so yes. So I would say that it is a subspace of R3. So this one is a yes. It said to show it, so whatever. All right, so in example 4, if you have this definition here, x and x plus 1, where x is a real number, is it a subspace of R2? Well, so to be a subspace of R2, that means it has to stay, two dimensions right there. And so, I mean, it does, but if I try to prove, for instance, like the 0 vector, all right, if I let x be 0, that's how I'm going to get this guy to be 0. But when I do that, I would get 0, 1. And so that's not the 0 vector. If I let x be -1, so x is -1, I would get 0 down here, but then I get -1 up here. So there's no way for me to get the 0 vector. So that is a fail. Okay, so no, it doesn't work. All right. Also, if you took something like if you wanted to try to do step 2, you could say, oh, I'm going to choose 5 and 6 because 5 and then 6 is 1 greater than that. If you add something like, let's say I add 10 and 11. So the answer has to follow the same format as this guy right here. All right, so you get 15 and you get 17. Well, 15 and 17 are not 1 apart. It's 2 apart. So it fails. This guy right here fails. That should have been 16 if it was going to follow this pattern right here. Okay. All right. So basically a shortcut for determining subspaces is like we were doing, show that those 3 things work, and that's it. So example 5, we just have these last few little things right here. This is like one of your homework problems. It says, let W be the set of all vectors in this format shown, where A, B, and C are arbitrary real numbers. Find a set S of vectors that spans W, or give an example to show that it's not a vector space. So, first of all, let's check and see would I get a vector space. All right, so if I let's say step 1, let's let A, B, and C all be 0. Then I would get the 0 vector, so that seems to work. Step 2, I'm going to do a couple things here. Let's see. Let's say I let A be 3, B be 2, and C be 1. All right, and that's going to be like 1 vector. And then if I plug those things in to my formula right here, A is 3 and B is 2, so 3 minus 2 is 1. B is 2 and C is 1, so this right here, so 2 minus 1 is 1. And if I follow the other formats, I get -2 and 2. All right, so I'm going to call this one my vector U, because that vector is in this space right here. And then I'm going to let A equal 1, B equals 4, and C equals 2. All right, and when I do that and plug it into my formula here, this is a vector that I get. I get -3, 2, 1, and 4. Okay. All right. So these are both things in this like little space right here. All right. So it's going to be my V. If you do U plus V, all right. So if I do U plus V, I get -2, 3, -1, and 6. So if you would go back and figure out if this works, all right, so I can tell right away that B is 6, all right, and so let's see about that. So B is 6, let me see if I can figure anything else out. A minus B, so let's see, I'm going to write down here, but you don't have to write it down. So A minus 6 has to equal -2, right, because that's the answer up there. So that would mean that A was 4, right? And let's see, C minus A, so C minus 4 has to be -1 right here. So that means that C has to be 3. Okay, all right, so that would be fine, right? A is 4, B is 6, C is 3. So it turns out that I can make this work. So let's check and make sure. If A is 4 and B is 6, 4 minus 6 is -2. If B minus C, 6 minus 3 is 3, yes. C minus A, so 3 minus 4 is -1, yes. And the last one is B, yes. So I can figure out that it does follow the format. And also if I multiplied by a scalar, it would work as well. All right, so let's do this last little part right here. So it is a vector space. So find a set S of vectors that span W. So to do that, I want you to notice what is in this original piece right here. If I kind of rewrite that and line everything up, I have A minus B and no C. Then on the next row, I have B minus C, so B and then minus C. Then C minus A, so I have -A plus C. And then lastly, B. If I turn that into vectors, my first vector right there is 1A, nothing for A on the next row, and then I have negative 1a, and then I have nothing for a right there. Well, that's my first vector in my span. All right, then for the b's, I have negative 1, 1, 0, and 1. And for the c's, I have 0, negative 1, 1, and 0. So it turns out, it says find a set S of vectors that span W. So this is the set of vectors that span W. All right. All right. So the last two examples, examples 6 and 7. So in example 6, is it a subspace of R3? So again, look at what you're trying to be a subspace of. So to be a subspace of R3, that means a 0 vector has to be there. So we saw one like this earlier. If I'm going to get the 0 vector, I think I would have to make A be 0. Well, if A was 0, that would never be 0. If I made A negative 1 to make this 0, then this would never be 0. So this is a no. I can't have the 0 vector. All right, and the last one here, the set of H is a set H of all matrices in this format, a subspace of a matrix 2 by 2 matrix. So this is really just a really basic thing. So they're trying to say, like, if you make a matrix with, A and B are certain numbers, and it goes in this format right here, if you add two matrices like this, do you get something that's a 2 by 2 matrix? Well, yeah, if you add a 2 by 2 to a 2 by 2, you get a 2 by 2. If you multiply it by a scalar, do you still have a 2 by 2 matrix? Yes, I mean, it could be all zeros, but yes. And could you get the zero matrix? Well, yeah, because you could make A and B 0 and they would all be zeros. So all three things work. You can get a 0, you can add, and you can multiply by a scalar. And all of those can produce a matrix that's a 2 by 2. All right, so as long as you can think of all those three things, then something is a subspace. And again, it just matters what you're trying to be a subspace of to whether or not it's real complicated or not. Okay, and there's your homework down there. I changed it up a little bit, so make sure you do those problems there for section 4.1, and I'll talk to you later.